Hello, Integrated Math 3 and Integrated Math 3 Plus. Welcome to lesson 16-4. So last time we were learning about trigonometric functions. Last week or so, we've been learning about sinusoidal curves, the graph of y equals sine alpha and y equals cosine alpha. I've been playing with all those guys. Today, we're going to go a little next level, and we're going to do transformations. Now, transformations on trigonometric functions are going to be a heck of a lot like the transformations on other functions that we've done. There's going to be one or two new little moments, though, so watch out for that. So you guys know the deal. You know that A stretches things vertically, right? It does those vertical stretches or compressions. If it's greater than 1, it stretches it. Smaller than 1, it squishes it, compresses it. You know this. It's not a surprise to you. You know about H, X minus H. Remember that minus sign is there, so it's always the opposite. And you know that causes horizontal shifts. You know K. K is familiar with you. K is on the outside, that plus K. You know it does your vertical shift, shoves stuff up and down. But we have a new guy today. C. There it is. C is a special guy. He's special, okay? This new parameter C shifts things a little bit. What C does is it actually affects the period of your function. And it's actually not the relationship you think it is. Remember how H was the opposite of what we thought it was doing because it was a minus? C kind of does that too. The deal is that C is actually equal to the parent period divided by the transformed period. And we're going to play with this, and you'll start to see how C works, and we'll play as well with the other parameters, which you kind of already know they work. But we'll play with C a little bit, and I'll help you understand what's going on with C just a little bit better. So C is the new guy, and C is going to affect the period of our function. So screw talking about it. I'm going to show you. That's right. Question number 1 on student activity sheet 3. You have a lovely table there that wants you to explain, hey, what does A do? What does C do? What does H do? What does K do? You probably know what some of these things do. And of course, some of these are going to be, we've got one that's a little bit new. So what I'd like you to do is just take a moment, hit pause, write down the few that, hey, I know it's going to do this. Go ahead and write it down on the ones that you know, A, H, and K, and then hit play when you're ready to check your work and also when you're ready to discuss C, because C is special and it's new. So go ahead and hit pause, make a few notes there on your table, and then hit play when you're ready to check your work and finish it off. All right, so I could use sine or cosine to demonstrate this. Just to make it easier, I'm going to use sine because it's convenient and it's there. And I'm going to start messing with these guys. Now, my default is that H and K are 0. I'm not adding or subtracting anything onto this. And that A and C are both 1 because you know if you multiply by 1, you don't change anything either. So let's go ahead and play with the sliders. Again, you already knew what A was going to do. A does vertical stretches. So if I increase A, oh my gosh, if A is greater than 1, yeah, that's definitely a vertical stretch. Looks like I made it 7 times as tall as it was. You can see here my amplitude was 1, but now my amplitude is 7. So yes, it definitely does a vertical stretch. You know that if it's less than 1, if it's between 0 and 1, that it's going to compress it. Yeah, that's not a surprise to you, right? So because my A is now 0.6, it compressed my wave, it squished it. Negative. What if A is negative? You know what's going to happen if A is negative. Oh, you know what's going to happen if A is negative. If A is negative, it is going to reflect over the x-axis. And look at that. I flipped my wave. That's right. Just hope you weren't on top of it when it happened. All right, you get the idea with A? Yeah, you already knew. Let's play with H and K. Again, you're familiar with these guys. You know that if I have alpha minus 40, it's going to shift 40 units to the right. If I have alpha plus 40, or we could say alpha minus a negative 80, I guess we'll put it at 83, then it's going to shift to the left. So you know this was not a surprise to you at all. I'm going to put that back at 0 just because I should. And you know what K is going to do? K is going to shift up and it's going to shift down. So if K is positive, it shifts it up. If K is negative, it shifts it down. All right. Nothing like earth-shattering here. Okay, so I'm trying to put things back where they go. I'm doing not the best job of it, but I'm trying. There we go. Sweet. Oh, my H is still a tiny bit off. Go back. I can't get it to 0. Oh my gosh, I can't get it to 0. I'm going to make it 0. Oh, now let's talk about C. Remember how we said that C, and I'm going to make a little note of this over here. We said that C was equal to the parent period divided by, what did we say in that last slide? We said something. Oh, hang on. Oh no. Oh, I'm making a mess. Guys, I'm making a mess. I'm sorry. What that last slide say? That last slide said that it was the parent period divided by the transformed period. There we go. I didn't have the words right. Now I have the words and it's okay. So we're going to say that the parent period is divided by the this is terrible, transformed period. Which, by the way, means you could rewrite it. If you multiplied both sides by the transformed period and divided both sides by t, you could also write it this way. You could say that your transformed period is equal to your parent period divided by c. All right. Now that we have that established, I want to point out a few things with this particular function. Now, for this particular function, my parent period is going to be 360 degrees because if you recall, that's what started all of this, right? When we did y equals sine alpha, we noticed that it took 360 degrees to get all the way around the Ferris wheel, which means my wave is going to repeat itself. Oops, sorry about that. My wave is going to repeat itself every 360 degrees. That is important to note because watch what happens with C. Check out C. Right now, C is set at 1. But if C is greater than 1, it compresses my wave. Yes, it has a horizontal compression. So if my C is greater than 1, my period actually got smaller. Yeah, my period shrank. If my C is greater than 1, I'm going to put it like over here, then my period grew, didn't it? So check it out. Right here, you can see, and just to give you an idea what happened, we just now set our C, where do we set? We set our C at 0.5. So if I were to do 360 divided by 0.5, that should give me my new period. Hang on, I got a calculator here. 360 divided by 0.5. And that tells me that my new transformed period is going to be 720 degrees. And look at that. Sure enough, when C is less than 1, between 0 and 1, my period got bigger. This is very important to notice. You might want to make some notes of this. I know you don't have a ton of space on that table, but you want to make some notes there about C. You guys are pretty familiar with A, H, and K, but you want to make some notes there about C because this is about to become super handy. If I use a different color, just to kind of demonstrate. And remember how we said if C gets bigger? So if my C is, I don't know, I'm going to make my C go all the way up to 4. Oh, yeah. So if my C is 4, take a look. Because my C is greater than 1, it squished it down. Why? Well, because that 360 degrees is getting divided by C to give me my new period, right? Ooh, that means in this case, I'm doing 360 degrees divided by 4. And again, if you grab a calculator, because that's what calculators are for, you can do 360 divided by 4, and you get 90 degrees. So when my C is 4, I have a period of only 90 degrees. And you can see every 90 degrees, my wave repeats itself. So C affects the period of your wave, and it's doing the opposite of what you think it should. The bigger C is, the smaller the period becomes, and the bigger C, and the bigger C the smaller the C gets, the bigger the period becomes. And it's because of that inverse relationship. It's because you guys remember when we did the whole inverse relationship thing? What unit was that? Oh my gosh. Unit 7? Unit 8? I don't remember. It was way back in the day. But we did the whole inverse relationship thing, which means as C gets bigger, my transform period gets smaller. As C gets smaller, my transform period gets bigger. They're doing the opposite of each other. Now, this may seem like I took a lot of time to explain that, but there's a reason. And it's because it's about to help you. It's about to help you on question number 2. Now that you got that table filled in, you have so much junk on that table. I would like you to answer question number 2. Go for it. I would like you to find the period. Now notice there's a lot of stuff on here. But all it's asking you to find is the period of each function. I'm not asking about shifting or any of that stuff. I just want to know about the period of the function. So you're going to want to find your C value and use it to help you find your new period. So go ahead and hit pause to work these out, and then hit play when you're ready to check your work. All right, people, I need my pen. I need a pen. I want to write in purple because it's me. Come on now. All right. So let's take a look at this first little guy. I'm looking for my C value. And there he is. There's my C value. Now I know for the parent function cosine, it's 360 degrees, but I also know that if I want my new period, it needs to get divided by my C value. So I'm going to divide that by 3, which gives me 120 degrees. And that means I'm going to drag this bad boy. Pop him in there. Yay. Let's look at this next guy. This next guy is a little more complicated, but again, I'm looking for my C value. There it is, that 1/3. And again, our formula said if I want my new period, I need to take my 360 and divide it by 1/3. Now this does look weird, right? Because you have a fraction within a fraction, and that's not cool. Remember that with fractions, you don't need to divide. You just need to multiply by the reciprocal. And the reciprocal of 1/3 is 3. So I'm going to grab my calculator. 360 times 3 in this case gives me 1,080 degrees. Sweet. So my new period is 1,080 degrees. Yay. Come back to my pen. Let's do the next one. Again, I'm looking for the C value. And there it is. Hey. So there's my C value. And again, I know that for sine, the parent function sine, the period is 360 degrees. But it's going to get divided by my C value. So divided by 0.5. Y'all have calculators. That means if I do 360 divided by 0.5, I get 720. Drag it over. Boom. And last but not least, I need to find my C value. There he is, hanging out in front of my alpha. And that means my parent function is cosine, which is usually 360 degrees. Divide that by my C value, which is 2, which means I have a period of 180 degrees. Dun, dun, dun. Boom. Shall we double check it? Shall we check it? Oh, yeah. Yeah, we're amazing and magical. So this actually wasn't that bad. It does mean, though, that the period for all of these have changed. Like last lesson, we were like 360 degrees. It repeats itself every 360 degrees. But these functions don't do that. This function is going to repeat itself every 120 degrees. This function is going to repeat itself. It's got way stretched out. It's going to repeat itself every 1080 degrees. Oh, it got really stretched out. This guy, less than 1. So sure enough, its period also got stretched to, it's going to repeat itself every 720 degrees. And this guy right here actually shrank, right? My C was greater than 1, and so my period shrank. It got compressed, and my function wave will repeat itself every 180 degrees. So it did do all the things that we felt like it should have done. Yay! Are you ready to go back to some more traditional stuff? I think you are. Yay! So we were talking about sine alpha and cosine alpha. And do you remember last time we talked about how they were actually the same? They were just horizontal shifts of each other. I think last time we wrote, we were like, this is so cool. So we wrote that sine alpha was equal to cosine, and then we put alpha minus 90 degrees, right? Because we were like, it does, sorry, my alpha went funky. It does a little 90 degree. In order to make this guy match this guy, we have to do like a right shift of 90 degrees. But what if I want to go the other way? And that is what question 3 is asking you for in your student activity sheet. What if I don't want to know what sine alpha equals with respect to cosine? What if, and I'm going to do a new color. What if, I want a pretty color. I do use a lot of red because it's at the end of the spectrum. It's easy to use. Let's go like a teal. Yeah. What if instead I wanted to write cosine alpha in terms of sine alpha? Go ahead and hit pause. Take a few moments to give it some thought and jot that down on question number 3, and then hit play when you're ready to check your work. It's not that bad. It's not that bad. So we said I could either, oh, hang on, I want my little arrow back. There we go. We said you could either take your cosine and shift it left 20 degrees, or pardon me, 90 degrees in order to get sine alpha. But doesn't that mean that instead you could, I'm going to try that again. We said last time that you could take your cosine alpha and shift it right 90 degrees to get it to match cosine. Which means going the other way, I could take my sine alpha and shift it left 90 degrees in order to get it to match cosine alpha. So that means cosine alpha equals sine alpha plus 90 degrees. Oh, remember how H is always doing the opposite of what we think it should? Yeah, that just happened. There's another important piece of information you need to know here, and you might want to write it down on your notes just so you know. It's just a terminology thing. We know that H is a horizontal shift. We're like, it shifted left 90 degrees. And last time we said it shifted right 90 degrees. We're real familiar with H and used to calling them horizontal shifts. But you need to know this. This is critical. When we refer to trigonometric functions, we don't often refer to them as horizontal shifts. We often call them phase shifts, which just sounds cooler. Let's be just honest about that. Horizontal shifts are usually called phase shifts because the functions are periodic, right? Like the function keeps repeating itself. And so the phases of our graph have been transformed. So just keep in mind, I don't want you to freak out if you see phase shift. Phase shift means horizontal shift. These mean the same thing. We just usually use the phrase phase shift when we're talking about trigonometric functions. It sounds cooler as well. So get used to using it because it just sounds awesome. One other little thing you need to know, you remember we learned about midline in one of our earlier lessons, the midline of our periodic function, how it was literally the line in the middle. You also saw that we referred to y equals sine alpha and y equals cosine alpha. We refer to them as sinusoidal curves. So also you should know that sometimes the midline is called the sinusoidal axis because it's the axis that your wave is bouncing up and down and up and down and up and down with it in the middle. It's kind of like the axis of your wave there. So we often call it a sinusoidal axis. It's still also called a midline. I like the phrase midline because it literally is the line in the middle, but it is sometimes called a sinusoidal axis as well. You should be aware of that. You should know that. Wow, so much new terminology. Same old stuff, new terminology, right? Good times. All right, here's what I would like you to do. Question number 4. We're moving along here. I feel like we're trucking right along. If we move over to question number 4, I want you to look at these 2 graphs. These 2 graphs are also on your student activity sheet. They're on question 4, and so they're right in front of you, which is very convenient. I'd like you to look at these 2 graphs, and we kind of played with these graphs as we were testing stuff on the parameters earlier. We flipped things, right, and we stretched things out. I'd like to know, I have 2 questions. I have a couple questions for you. First, I'd like you to tell me the amplitude of each of these graphs. What's the amplitude of this first graph? What's the amplitude of the second graph? I would then like you to tell me, what is my A value, not alpha, what is my A value for each of these functions, all right? And then I'd like you to tell me how my amplitude and my A value are related. Go ahead and hit pause to jot down your thoughts on question number 4, and then hit play when you're ready to check your work. So start off finding the amplitude. To find the amplitude, the first thing I did was I kind of drew in, oh, I don't have it here. To help me out, I kind of drew in the midline. You didn't have to do this, but I find it's helpful to draw in the midline. And I noticed that the midline is my x-axis, so that made things a little easier. So when I was finding the amplitude for this guy, my amplitude, remember how we counted from the midline to my maximum? And it looks like from my midline up to my maximum is sitting at 2. So from 0 to 2, looks like my amplitude is 2. If I do the same thing over here, and again, you don't have to, but if you want to draw on your midline, which is basically just your x-axis, and again, I'm going from my midline to my maximum, and it looks like from my midline to my maximum, well, according to the graph, is 2. So again, this guy also has an amplitude of 2. So they both have an amplitude of 2. The next thing is a question asked us for our A value. So let me take a look at this. Looking at the function itself, remember A value was the guy out in front, and that's a 2. So this guy has an A value of a 2, and this guy has an A value of -2. So let's see if we can answer the last question here. How are the amplitude and our parameter related? Well, guys, take a look. For this first one, our amplitude and our A value, our parameter A, is the exact same, right? These are the exact same. For this one, my amplitude is still 2, but my A value was a -2. Because if you remember, the negative flips the function. And you'll notice this red function is flipped from this guy over here. Yes, it is. So what's the deal here? What's the dealio? The deal is, the reason we use A for the A value is because it's actually, oops, sorry, I'm having a little issue here. It's actually the amplitude of our function. Although I'm going to rephrase that. The absolute value of your A value is the amplitude of the function. And actually, I'm going to make a note of that because that feels important. So I'm going to say that my amplitude equals the, oh my gosh, that looks bad. I'm going to fix it. It looks awful. That's better. That my amplitude is the absolute value of my A value. Yep. Wow. Absolute values are pretty easy to find. That's convenient. I have one more. I have one more question before I'm done torturing you guys. This wasn't a very long lesson. It's all good. One more. Question number 5, which is right below question number 4, just down the bottom of the page there. And here we go. This graph shows us a lovely sinusoidal curve, but check out where your sinusoidal axis is. Look at this. They drew it in for you, which was very nice. So they said that your sinusoidal axis is actually at y equals -2. What happened to your curve? And if you can figure out what happened to your curve, then you can answer the question. Take a thought, what happened to your wave, what happened to your sinusoidal curve, and use that to help you write a function rule for this graph. It's supposed to be the original is y equals sine alpha, but something happened to this graph. And we're going to use these, and please notice, not only did my sinusoidal axis change, you might notice that my amplitude changed, that my period changed, that there may have been a little bit of a phase shift here. Yeah, there are a lot of things that happen to this function. So go ahead, hit pause, work this out best you can, and then hit play when you're ready to check your work. All right, to help me do this, because I'm about to lose my mind, to help me do this, just over here, I'm going to write the original, right? We had y equals a times the sine of c times alpha minus h, and then a big plus k. And I'm just doing this to kind of help me figure out all my pieces and where everybody goes, because there is a lot happening here. There's definitely a lot happening here. All right, let's start with some of the easy stuff. I'm going to start with k because it did mention the sinusoidal axis is at -2, which means you can tell if my sinusoidal axis is at -2, my function got shoved down 2 units. This means that my k value is a -2. Great, that was easy. All right. I'm going to then move on to the next easiest thing, which is my a value over here. Sorry, my pen gets a little excited sometimes. So I'm going to start with my a value over here. Remember that a was the same thing as your amplitude, our absolute value there. So I'm just going to come over here. I'm going to come over here and I'm going to count. And I'm like, okay, well, I'm at -2, but to get to my maximum, so I'm at -2, but I had to go 1, 2, 3, 4, 5 units to get up to my new amplitude. So that says to me, I'm pretty sure my a value is 5. Sweet. All right. We have a little more work to do for the others, but nothing terrible. Let's see. Let's check that horizontal shift. I'm pretty sure that this is supposed to be at 0. That is not at 0, right? That we're supposed to say here, we start at 0 and we go up and we come down. And that is not at all what happened. How far off did we get? Well, it looks like we're off by what? It's counting by 20s, so 20, not quite to 40. So what, about 30 degrees? I look like we're about 30 degrees off. In fact, it looks like if I shifted right 30 degrees, doesn't it? So if I shifted right 30 degrees, then that means my h value is, well, 30 degrees. And so my phase shift is 30 degrees. So let's now play with c. All right, c, that's a sine function. So we know that it should be 360 degrees, but it's not. But remember that we can find our c value by dividing by the new period of my transform function. So I'm going to count tops to tops. I think that'll make it easier. I like counting tops to tops. It's better. So I'm going to count from here to here. And it looks like I've got, remember it's counting by 20s. So that's 20, 40, 60, 80. Didn't quite make it to 100. So what about? Didn't quite make it to 100. I'm trying though. It looks like, yeah, about 90. Yeah. Okay. So 20, 40, 60, 80, not quite to 100. So we'll stick with 90. So we'll say that should be 90 degrees. is my transformed period. And fine, 360 divided by 90 gives me a 4. So it looks like my C value here should be a 4. So fine, I have y equals 5 times the sine of 4 times alpha, since we're using alpha instead of x, minus 30 degrees. And then I have a minus 2 on the end. Huh. Shall we check? Shall we check to see how we did? I'm gonna have to erase this though. I know it's so sad because it's so beautiful. Oh my gosh. Yeah, we're gonna erase that because now I have a big fat mess. Boom. How'd we do? I want my arrow back. Got my arrow back. Oh, we did beautiful. Oh, we did such a good job. We're amazing and magical. Hey, I'm impressed. All right, guys. As always, I hope you found this helpful and I hope you found this useful. If you've got questions or concerns, please email me or pop into my office hours. Charlotte and I will be here waiting for you. And I'll see you soon. Bye.